So, hi and welcome everyone to our fourth exercise course, where we will accordingly talk about exercise sheet number 4, which is about the topic subgradient, projected gradient descent, and we still have one question or one exercise left from the previous exercise sheet, namely the practical exercise. But I would suggest that we go over the two theoretical exercises, and then we will make sure that we have still time to look at both practical exercises, the one on the current exercise sheet and the one on the previous one. All right, so what we want to start first is an exercise about subgradients. Yeah, so we had these two extensions of the gradient descent, namely the one where we also incorporate subgradients, which are a substitute for the derivative or the gradient when the function is perhaps not differentiable at some point. Then we saw, well, this subgradient is a suitable substitute because it's essentially having the one characteristic property we want in order to do the analysis, which is then guaranteeing that we have a suitable convergence rate of the subgradient descent, is it then? Yeah, and this property is more or less similar to the first order characterization of convexity when we have differentiable convex functions. So we will also have a look at this property, which is more or less the formula 1. But let's first start with the part A of this exercise. So what do we have here? We have as our objective function simply the Euclidean norm of the input vector theta, so not squared. So this is important that it's not squared. And if it's not squared, then the function is actually not differentiable at the point 0. And this is, of course, somehow bad. If we somehow combine objective or this Euclidean norm with other functions, then it's definitely not good if we don't have here a derivative in the 0 point. But it turns out that we have subgradients available for this point, and the set of subgradients is the following set S of theta. It consists of all z. So to be more precise, these are, of course, d-dimensional vectors, which are having only one, or which need to fulfill only one property, namely that their Euclidean norm is bounded from above by 1. So essentially, this is the unit L2 ball. Not essentially, it is unit L2 ball. So any point in the unit L2 ball we will see is a subgradient of the function f in the point 0. And then we will ask for, well, what are the subgradients of the function when we are not looking at the 0 vector? What happens then? And as I already revealed more or less, everywhere else it is differentiable, and we can compute the derivative or the gradient explicitly. All right, so let's start. Let's recall first of all what this subgradient property is, or rather, when do we call a d-dimensional vector a subgradient of a function at some point? And the definition is simply here. Yeah? So we call this Z subgradient if it fulfills this inequality for every theta prime in theta. Yeah, if theta corresponds to the domain of the function f. Of course, the domain is completely RD, then we have here RD. So what is this telling us? This is essentially telling us that for some function f, yeah, might look like this. Or let's use a different color perhaps. So for function f, is that one. We have that at some point theta, which we pick, or perhaps here is our, now red is already occupied. Let's take blue. This is the theta. Then the subgradient property is telling us when we look at this linear function, in theta prime, you see it's linear in theta prime, theta and theta are fixed. Then if we can find a slope, which is essentially specified by the z, by the subgradient, we can find a slope of this linear function such that the entire linear function is below the function f, then this slope, or this vector corresponding to the slope, this is a subgradient. And you see in this example, there is perhaps not a unique solution to that. There might be multiple z's which are fulfilling this property. So here I picked one slope where this is obviously the case, but we can also make the line a bit steeper, and still the entire linear function will be below the function f. And this is the same, or almost the same, characterization of a convex function if it is differentiable. Because the first order characterization of convexity is telling us this inequality here is true for z being the gradient, being this gradient of f at that point theta. So perhaps this is worth recalling that. So if f differentiable, then z must be the gradient of f at the point theta. There's only one subgradient, and it is the gradient at that point. Okay, now so this is a quick recap on what the subgradient is about. Essentially a substitute for the gradient in case we don't have a differentiable function. Coming back to our concrete exercise, where we are now looking for the function f at the Euclidean norm, we want to check that indeed this unit L2 ball is the set of subgradients, all these available slopes more or less. All right, then let's consider the case that theta is the zero vector. We have an arbitrary value or vector z, which is in the unit ball. Yeah, so meaning that its Euclidean norm is bounded from above by 1. Then, yeah, let's start with the right-hand side here of the subgradient, yeah, where we have f theta, or this linear function of the theta prime. This is what we see here. And now let's first plug in what we have here. This here is our function. It's theta Euclidean norm, but theta is the zero vector, and the zero vector has obviously Euclidean norm of 0. Okay, what can we see moreover? This is 0. We can also see that this here, if theta is the zero vector, is also 0. And when we compute an inner product with the zero vector, we can be sure that this is still a 0. So what remains is only the inner product of z and this theta prime. All right, then recalling what we know from linear algebra, and there is a well-known inequality which is giving us an upper bound for the inner product between any two vectors. It's the Cauchy-Schwarz inequality, which is stating that the inner product of two d-dimensional vectors, x and y, is always bounded from above by the product of their Euclidean norms. Well, obviously, what do we use here? We use here for x, we use z. For y, we use theta prime. And yeah, we get this inner product is bounded by this product of Euclidean norms, namely the Euclidean norm of z and theta prime. And now, what do we use now? We use that z is inside the unit ball. So this thing here is bounded from above by 1. So if we replace here the Euclidean norm of z by 1, we make this only larger or equal. So what remains is the Euclidean norm of theta prime, but this is obviously the function evaluated at theta prime, because our function is mapping a vector to its Euclidean norm. Okay, so what we see? We started with this linear function in theta prime, bounded it from above by f of theta prime, and well, this is exactly the subgradient condition. And this is true for any theta prime. Now, we haven't specified anything here about theta prime. We haven't specified anything about z, except that its Euclidean norm is bounded from above by 1. So we see, yes, the unit ball, or all vectors in the unit ball, satisfy the subgradient property. So they are definitely a subset of the subgradients. Now we have to think about, well, can there be more than that? Is it possible that perhaps a vector which is having not Euclidean norm bounded by 1, that this is also a subgradient? And we will see, no, this is not the case. So what we look at now is we look at the case that our z, now we take an arbitrary point which is outside the unit L2 ball. When it's outside the unit L2 ball, it means that it has Euclidean norm strictly greater than 1, because otherwise it would be inside the unit L2 ball. What does this mean if the unit or if the Euclidean norm of this vector z is strictly greater 1? This means that there must be one component where the ith value is strictly greater 1. Otherwise, we end up again inside the unit L2 ball. So what we can do is we can look at a specific theta prime, and the specific theta prime which we are using is the one where we have that the jth or all components are 0 except the one where the z is greater 1. But this is not. This is not true.
I have a question. Yeah, right about that part.
This is not true. This is all
right. Like if imagine a circle in 2D.
Yeah.
Then if we have the vector 1, 1, both components are not greater than 1, but they are not in the circle.
No. This is why I was hesitating after I talked about it. This is not true. So we have to fix this. So if z is greater 1, this is meaning that zi, the sum over them, this is greater 1. Yeah, this is for sure. So what we can then say is that yeah, exactly. So what we can say is that d times the maximal component of z, and let's call it zj. So j is the argmax of I. Yeah, we can infer this one. And from that, this is meaning that zj, that this is greater 1 over d. So what we can fix here, and I think this will work. Now we can find some, and now I called it j, now substitute it with I, doesn't matter. We can infer that there's at least one component which is greater 1d. And now what we simply do is we look at a theta prime. This is a d-dimensional vector such that all entries are 0 when the entry is not the I, corresponding to the entry.
I'm sorry, I'm still a bit confused because I just went over the 2D example again. So in 2D, it would be 1/2, right? The threshold that you specified.
Oh, yeah. So, sorry, we forgot to take the square root here, of course.
Okay.
Yeah, sure. You're right. Thanks.
Okay, thanks.
This is, we are not looking at the squared Euclidean norm. Yeah, you're right. So this is greater than square root d. Yeah, great. So no problem. We can fix this. Square root d. Yeah, thanks. Okay, now it should be fine. Yeah, so of course not forget to do the square root because we are not squaring. We are not looking at the squared Euclidean norm, namely the Euclidean norm as it is, and there we have to take the square root. Okay, so And now what we also need to fix is that the ith component of the theta prime vector, that this is simply square root d, I guess. Let's see. This will give us z1. Z1, this should be 1 then. The greater. And this is not working. Okay, then let me rethink a second. Okay, this is of course now not so nice. So nice. Okay, there should be a component which is greater than 1D. It's, I have no answer right now, because obviously my proof breaks down here. Yeah, my proof breaks down because of course here we have theta 1, this is a 1, but the Euclidean length of the theta prime vector is
Maybe we can come back to it later.
yeah, I think we should do this. So I'm pretty convinced that this is fixable. Yeah, so I'm very sure that the subgradients are indeed the unit L2 balls, but there's obviously a flaw in this argument here. Yeah, so I will rethink it later on if you have time. If not, then I will come back to that simply in the next exercise. Okay, yeah, so, but as I said, I am pretty convinced that this is fixable, and I guess there is another more convenient approach to tackle this. But okay, let's postpone this. So let's consider the case now that the theta prime is not a zero vector. And in this case, the function f is simply differentiable. Yeah, the function f, which is mapping a vector to its Euclidean norm, which is square root, not forgetting the square root, summing up the squared components. This is also what we forgot there, right? Squaring the components. And well, if we now fix one component of the theta vector and look at the partial or at the derivative with respect to that component, what do we have here? Well, yeah, we can go for our usual way to compute derivatives. And what do we get? Well, we will get derivative of the inner function with respect to that. This would be 2 times theta I, if we go for the ith component. And then we multiply this with the derivative of the outer function, and the outer function is the square root function. So that we will get here 1/2. From the square root, we would take one exponent, or we decrease the exponent by 1, so that we essentially have then the square root in the numerator, and what we plug in is the function there, and the function there is still the sum, the squared sum over the components. These are canceling out. This here is the Euclidean norm of theta. This is true for every component I, so this is what we see here. Yeah, so when we go for the first component, we get this here, and in all the other components, it's simply switching the entry of theta in the enumerator. So we can also write it quite conveniently in that way. And you see here why the theta equals 0 case is critical, because then, so if we would look at the case theta equals 0, well, here we would divide by 0, essentially. Yeah, this is the problem there, which is not happening if we look at the squared Euclidean norm, by the way. And well, this function here is convex. This is what we have shown on one of the previous exercise sheets in a quite general way, where we only assumed that the function needs to satisfy 2 properties. And the remark was there that all norms on the d-dimensional revalued numbers satisfy this property. So we concluded that all norms are convex, and in particular the L2 norm. So we know if the function is convex, if it's differentiable, there is only one subgradient at that point, and it is simply the gradient at that point. And as we just have shown, it's theta divided by the length of theta. All right, then let's continue. Now we don't have to care about this case where we have to exclude the z, because now what we look at is the function which is mapping a vector theta to its L1 norm. And the L1 norm, now with the absolute values, it's summing up the components, the absolute values of the components. And well, this is the Euclidean, the L1 norm. And what we want to show is that the set as theta here, consisting of all d-dimensional vectors z, which are such that the maximum absolute component is at most 1, and the inner product of z and theta is equal to the Euclidean, the L1 norm of theta. Now, this is a subset of the subgradient. The other direction, so one can show this is, in fact, exactly the set of subgradients, but the other direction is even harder than in the case before, where we had the flaw. So that's, we don't have to care about that. But for the, perhaps as a side remark, for the subgradient descent, it's essentially not relevant, or for at least for the theoretical analysis, it's not relevant to choose or to care about the choice of the subgradient. Any subgradient at a specific point can be used in the subgradient descent algorithm. So it's sufficient if we know at least one subgradient which we can pick then in the subgradient descent. All right. Then let's have a look at this case. We start again with the linear function in theta prime, which is occurring in the subgradient descent property. We plug in what our function f is. So we have it here above. It's the L1 norm of theta. And well, we use here simply the law of distributivity, and we can write it like this. Now we use that our z is in as theta, and if it is in as theta, it's telling us that this here is the same as this here. But here we have it with a minus, here we have it with a plus, so they are canceling out each other. And what remains is only the inner product between z and theta prime. Okay, then let's have a look at this inner product. Inner product is nothing else than multiplying the components of the two vectors and then summing up all of them, which is bounded. That this is always true. We make it only larger or equal if you write absolute values around this term. No? So this is quite elementary property, which is true for every real-valued number, also complex. And what we can then use is the it's essentially the triangle inequality applied d-1 times. So you know that a plus b is always smaller than a plus b in absolute terms is always smaller than the sum of their absolute values. And we use this here d minus 1 times, and we see, well, this is smaller than if we sum up all the absolute values of the product of the components von z and theta prime. Now we make this only larger, so what we also can use is that a times b for real-valued numbers, this is the same as if we would multiply their absolute values. Now this is what we do here. And we can make this smaller or larger or equal if you replace here for the zi the largest absolute component of the z, which is here. If we do this, we don't have any dependency on the summation index I, so perhaps I should have used here a j to not confuse you, because then I and I. Yeah, so this is a fixed value. So one of the components, or it might be multiple, but at least there is one which is in absolute terms the largest one. We can replace all of them by that one, and we make this whole thing only larger or equal. In turn, we can pull that value out of the sum. And what remains there is simply the L1 norm of theta prime, and what we know is that because z is inside s theta, this thing here is smaller than or equal 1. So we can bound it once again from above by simply the L1 norm of theta prime. But this is the function we are looking at. No? Function f is mapping a vector to its L1 norm. So we started with this subgradients linear function and theta prime with z as our candidate for the subgradient, and we have here it's smaller than or equal than f theta prime, which is exactly the subgradient property. We haven't used anything about the theta prime, so the theta prime was here quite arbitrary, and this inequality is true for all theta primes. So we have the subgradient property. And what is this now telling us? This is perhaps worth remembering for our practical exercise. It's telling us that for the Euclidean, I'm tempting to say Euclidean, L1 norm, it's the L1 norm we are looking at. For the L1 norm, we can always compute the subgradient for that thing by finding a vector z which is fulfilling these two properties, the orange and the blue one. What is a vector which is fulfilling this? It's simply the vector where in each component we take the sign function of theta I. Why is this the case? Well, let's have a look at z, which is component-wise given in this manner. Then, well, if we would look, so quite obviously, first of all, the orange condition is fulfilled, because sine, what is this again? It's having 3 values, depending on the cases. It's a +1 if theta 1 is positive, it's -1. If theta I is negative, and in the remaining case where it is 0, it is 0. Yeah, so it's giving us the sign of the input. And for the 0 input, we simply return 0. Okay, but as we can see, yeah, if the z components are either +1s, 0s, or -1s, if we consider the absolute value, yeah, this cannot be larger than 1. So the orange property is obviously fulfilled. What about the blue property, that we get the L1 norm of theta if we consider the inner product of z with theta? Well, theta, it's z1 theta I sine of theta I times theta I. This here is the absolute value of theta I. Why? Let's assume theta I is strictly positive. Then the sign is a +1. Absolute value is then equal to theta I. Assuming the case theta I is 0, well, then we are multiplying here 0 with something, which is also a 0. It's not so interesting, but the absolute value of that thing will also be 0. If theta I is negative, then the sign here is negative, so we flip the negativity to positivity, and this is exactly what the absolute value will do if we apply it on theta I. So you see, indeed, sine of a real valued number times the real valued number itself is simply the absolute value of the real valued number, and well, this is the L1 norm. So you see the blue property is also fulfilled. Yeah, so every time we have somewhere the L1 norm and we need to compute the subgradient of that, we simply can take the vector where we have component-wise the sign of the input. All right, so I have the feeling I get time trouble. So let's continue. All right, so next case. So this is interesting for combining subgradients in a suitable way. Namely, when we have a composition of functions, f1 till fm are convex, h is also convex and non-decreasing, and when we plug in rm, of course, sorry, exactly, yeah. So if we plug into the function g the function f1 till fm theta, yeah, then this is a composite function. So we have a composition here of function. And what we want to look at now is the case where we want to compute the subgradients of this composite function, and it's given, or we can at least compute or specify a subset of subgradients for that function. And it's first of all looking complicated, where we have all the subgradients of the fi functions, and we combine them with the components of the g function, of the zg function, zg subgradient rather, which is evaluated at the point f1 theta and so on to fm theta. And how can we see this? Let's take a subgradient of g at this position. Let's take subgradients of the fi's for every fi's. Then we start with h theta prime. Definition is we simply plug in the theta prime into the fi functions inside. Now we have that the function g1, g is non-decreasing, and all these zfi's are subgradients. Just to see this quite obviously, is the subgradient is telling us, well, fi theta prime is greater than fi at theta plus z fi transposed theta prime minus theta. Yeah, and this is what we do here component wise, and we make this only then larger, smaller or equal. Then we have here these complicated terms for each of the entries of the g function. And now we can once again use the subgradient property of the zg at this position. And this is telling us, well, g evaluated at some theta prime. Now we will specify what the theta prime is greater than g evaluated at f1 theta and so on and theta plus zg transposed and then theta prime minus again the theta, or the point at which we look at for the subgradient, and this is that one here. So the vector consisting of f1 theta and so on fm theta. And the question is, well, this is true for every theta prime. Which theta prime do we use here? And well, the theta prime we are using, this one here, this one is this here, right? The vector, this vector here, and which we also then see here. And okay, here we have the difference between two vectors. Here in this vector we have a sum, in fact, in each component. Now we do the subtraction of these, and what remains is only these inner products of theta prime and theta with the corresponding subgradient of the fi function. And now just writing it out, what is so with this inside the vectors, so by the way, the dimensionalities are all well defined. Yeah, the inner product will give us a revalued number in each component, so everything is fine here. So this is indeed not a matrix, or of course it's a matrix because it's a vector, but it's in fact a column vector. Yeah, what we have here. And well, what we could do is we can also write it in the following way. So what we will get is, when we do this inner product computation, we will multiply the first component with this component, the second component of ZG with the second component here, and so on. And we can conveniently write this like this. And what we see is, here we have again h theta. We started with h theta prime. We have here this inequality in between, and we see, okay, for any theta prime, we have that h evaluated at theta prime is greater than or equal than h theta some vector, inner product with this vector with theta prime and minus theta. But this is, again, the definition of the subgradient. So this thing here, this vector we have here, this is a subgradient. This is the subgradient, or one subgradient. But this thing, this combination, is exactly what we have in the set S of theta, where we again only use these two properties, that Zg is subgradient of the function g evaluated at these points, and the ZFIs are subgradients of the Fi's at theta. Okay, good. Then let's go on with that. So perhaps one side remark. Yeah, so this is quite convenient because composition of function, you can imagine that this is something occurring quite often, that you somehow combine these functions in a compositional manner. And if you can already compute or specify one subgradient of the components, namely the inner functions and the outer function more or less, then you can conveniently then say what the subgradient or one subgradient is of the composition function. All right, so then what we want to do now is we want to consider how to compute projections. So we had this projected gradient descent where we had the issue, or which was motivating us to also look today at an alternative way to projecting the iterations back onto the solution space. But we saw one example where computing projections is in fact possible in a closed analytical formula, namely for the L2 balls. And we showed this with a rather algebraic proof that we can compute the projection in a closed form, but there's also an analytical way how to derive such projections, or perhaps derive them in a closed form. And this is done by the so-called Karush-Kuhn-Tucker conditions, where we have the quite generic form of a constraint optimization problem, which is more or less very similar to our basic optimization problem, where our theta space or solution space is specified by a function g and a function h, such that the theta must be such that if we plug into the function g, the value must be at most 0, and if you plug it into the h, it should be 0. Yeah, and the initial goal is to minimize some objective function f. But of course, taking these restrictions, these constraints into account, which are essentially specifying then your solution space theta. And these Karush-Kuhn-Tucker's conditions, these are these 5 here, they are specifying when we can encounter a local minimum for this constraint optimization problem. And it revolves around the so-called Lagrangian function. What is the Lagrangian function? Here's a mu missing, sorry. The Lagrangian function, usually denoted by this calligraphic L of theta, lambda, mu, is the function we actually want to minimize, plus lambda times the first constraint function, plus mu times the second constraint function. And you can also consider the case where you have multiple constraint functions. Yeah? So then you have here multiple lambdas for each constraint, for each inequality constraint function, 1 lambda, and for these strict 0 constraints, you have 1 single mu value. Yeah, but here we only consider this case where we have only the 2. So in the part B of this exercise, we will actually look at also the case where we have multiple h function of that kind. And these Karush-Kuhn-Tucker conditions are the following. Yeah, so we can say for sure that theta prime is a local minimum for this constraint optimization problem if we can find these lambda and mu, or we can find 1 lambda and mu value, or for the case where we have multiple, then we have here all of these conditions multiple times for the lambda and mu values. And the first one is very similar to what we have to make sure if we want to find a minimum or an optimum in general with regard to the theta, namely if we look at the gradient of this Lagrangian function with respect to the theta parameter, plug the theta prime, this candidate for the local minimum, inside this function, and as well these lambda star and mu star values, we get here a 0. This is quite similar to what we would have if we wouldn't have any constraint, perhaps. Yes, and here you have here a similar condition. The second condition, so these lambda prime and mu prime, they must be non-negative. This should also hold when we have multiple constraints, multiple constraint functions. Then all of the lambda prime and mu prime factors are non-negative. The third one is that if we multiply the found lambda prime with the inequality constraint function evaluated at this local minima candidate, it should be exactly 0. The fourth one is, making sure that the constraints are really fulfilled for this local minima. So we have a constraint optimization problem with these 2 constraints, and the fourth one is taking care that the local minima is, of course, making sure that these are fulfilled. Then the fifth one, I have here just written very roughly, there are some conditions on the Hessian matrix of the Lagrangian. Again, here the mu is missing. Prime. It's quite similar. So it's a bit different, but still quite similar to what we know from our previous considerations, that the Hessian matrix is positive definite or semi-definite, and essentially it's very similar to what you have to check there. But we will ignore this fifth condition and simply assume it's fulfilled, which is in fact the case for every problem we will look at. And what we will do now is we will use this analytical way via the Karush-Kuhn-Tucker conditions to compute the Euclidean projection onto the Euclidean ball with radius b, where b is some value strictly greater 0. And in the lecture we did this already, but again with the algebraic proof, now we want to go this analytical way. And we can do this as follows. So we have to make sure to specify the functions we are looking at correctly, and then simply checking these Karush-Kuhn-Tucker conditions. So the function we want to minimize is the projection function. And to make life easier, we look at the squared Euclidean, the squared Euclidean projection. Because if we do not square it, we saw in the first exercise at the point 0, the 0 vector point, we have the problem that it's not differentiable. If we square it, no problem. It's differentiable everywhere. And whether we want to minimize the square or the function, if we have some non-negative function, doesn't matter. The minimizer will be attained at the same position, at the same vector. Then the question is, what are the constraint functions? And this is what I told you before. There is a correspondence between the solution space we are looking at and the constraint function. The solution space is in fact already specifying such a constraint function. Namely, if we look at the following constraint function where we map a vector theta prime to its squared Euclidean norm and subtract from that b squared, then if this is smaller than 0, then this is telling us that theta prime is in fact inside the Euclidean ball of radius b, because only then the condition will be fulfilled. And what about this equality constraint? Well, we can also specify a trivial constraint. Maybe we can say, well, this function h is simply the 0 function, and then every theta prime we plug in here is already fulfilling this constraint here. Because if the theta is like this, we are in fact only interested in these inequality constraints, which is given here. We could also look at the case where the Euclidean norm is exactly b. Then we wouldn't have here the g function, which we could also set then to the 0 function, and then specify the h theta prime as this difference here. Okay, what is the Lagrangian? The Lagrangian is above in this case. So we add to the function f lambda times the inequality constraint function g plus mu times the equality constraint function h. This is a 0 function. This is 0. We plug in the definition. For f, it's the squared Euclidean norm between theta and theta prime. Theta prime is here our input vector for which we want to minimize. We plug in the g function, the inequality function, which is given here. We use that we can write the squared Euclidean norm simply as the inner product of the vector we are having inside the Euclidean norm, and the vector here is the difference between theta and theta prime. Here the same, here just the vector is theta prime. And well, multiplying out, which we have done now a couple of times with this inner product term, we get to this expression here. And now we have it in a quite nice way. So we have stated it in a convenient way, let's say, the Lagrangian function, where we can compute the derivative with respect, or the gradient with respect to theta prime in a convenient way. What should we need to do to check the first Karush-Kuhn-Tucker condition? Namely that if we plug in the local minima theta prime, it should be the zero vector. So there should be a bold zero indicating that this is a vector. Okay, then also here everywhere it's a bold zero. Now it's always a zero vector. So the gradient with respect to theta of the Lagrangian function, what do we get? The gradient of this thing with respect to, here you have to be, so let's rather write here theta prime, that you are not confused with here the different notation. So the gradient with respect to theta prime of this here is 0, of this thing with respect to theta prime is minus 2 times theta, and of this thing, and then we multiply this simply by this factor 1 plus lambda. This is 2 times theta prime, and well, this here is also 0. And well, this is what we get here. So minus 2 times theta plus 2 times 1 plus lambda star, because we have here the lambda star plugged in. And then for theta prime, we plug in the theta star. Now this needs to be 0 by the Karush-Kuhn-Tucker condition. And we can solve this equality with respect to the theta prime, because this is at the end what we are interested in, the theta prime, the minima. And we see, well, the theta prime is of this kind, theta divided by 1 plus lambda star. Okay, so this is essentially telling us how the local minima is looks like in dependence on the lambda star. But the lambda star is still not specified yet. But we can specify it by considering the third Karush-Kuhn-Tucker condition, which is telling us lambda star prime multiplied with g theta prime should be 0. And what we will do is, if the theta, the term which we want to project, is already inside the Euclidean ball with radius b, this is what this is telling us, we set it to 0. The lambda star is set to 0, and then obviously this condition is fulfilled. Multiplying something with 0 is equals 0. And if this is not the case, if theta is having a Euclidean norm greater b, we now specify an explicit condition on the lambda star, and we get this by the following equivalence consideration. So we have here the definition of the g function, which is simply the difference between the squared Euclidean norm of the input with the squared radius of our Euclidean ball. We use here the representation of our theta prime, which we have derived from the first Karush-Kuhn-Tucker condition. We plug it in here. We multiply on both sides, or divide on both sides, with lambda star. This is what we can do because we are considering the case where this is strictly greater 0, because the case where it is 0 we already had. We pull out the 1 plus lambda star in the denominator here in the Euclidean norm. This is a scalar which we can plug out or pull out, and don't forget the squaring. And well, with a couple of manipulations, we will see lambda star is given by this form. Yeah, so it's the Euclidean norm of the theta divided by b minus 1. We can do a quick sanity check that this is true. Let's plug in lambda star here in this line here. Then we will see 1 plus this thing minus 1. The ones are canceling out. So we have theta Euclidean norm in the denominator. It's canceling out with the thing in the enumerator. And what we are left with is b squared in the enumerator. And this is finally subtracted, or from this we subtract b squared itself, which is then 0. So we see everything is fine. This is indeed what we get if we solve with respect to lambda star. Now we combine everything what we have, that the theta prime is of this kind due to the first Karush-Kuhn-Tucker condition, and that we set lambda star to 0 if the theta is already inside the Euclidean ball of radius b. And if it's not, then the lambda star is like this. Well, this is what we get here. But if we combine now everything, theta star is of this kind. When it's inside, when this theta is inside the b, we set lambda star to 0. So theta divided by 1 is theta itself. In the other case, where this is greater, the lambda star is of this kind. We plug in the lambda star in this representation here, and what we get is exactly this representation of the theta star, b times theta divided by the Euclidean norm of theta. And of course, there are two other conditions which we need to check, and it's quite clear, lambda star, that this is non-negative, is fulfilled. Here it's 0. In this case, it's also greater 0, simply because in this else case, the enumerator is greater than the denominator. So we have here something which is at least 1. We subtract from that a 1, so we are having a non-negative value there. And the fourth condition, that the found solution, the local minima, theta prime, is fulfilling the inequality constraint. Yeah, this is also easy to check because, well, in this case, it is inside the ball. In the other case, we make sure that the length of the theta prime will be exactly b, so that the inequality constraint is also fulfilled. All right. Yeah, sorry, I think the first part, this is of course my fault. I apologize for that. I should have been here more careful. We lost here a couple of important minutes. So let's do it like this. I would suggest that we now go to the practical exercise quite quickly. I mean, the part B is very similar to what we have seen for the Karush-Kuhn-Tucker conditions for the Euclidean projection on the Euclidean ball. Nevertheless, we will talk about it in the next exercise course. And because I already postponed the practical exercise last time, I don't want to do this again, so that we have now at least 15 minutes to talk about that. All right. So again, sorry for the bug in the first part, but I will take care of that later on and let you know. So good. So exercise number 3. Right, what we wanted to do here is to look at a quite common machine learning problem, namely, or it's also a statistical. So the statisticians will be angry if I call this a machine learning problem, because it's essentially a statistical problem. Or so it's a quite common problem in science. Let's put it like this: that everyone is happy, but in particular also for machine learning. And what is it about? It's about least square estimation, where we have, so unfortunately the things here are not rendering it as I wanted. What we are having is we are having a data matrix, which is storing data about whatever you want. So in our example here, it will be the weight or height. How was it again? It will be the height. So it will store the height of different persons. So you can also store additional information about the person, but we will be focusing on the case that we have here the height. And we assume that we have capital N many persons, for which we simply measure their height. And what we want to do now is we want to conclude whether we can find some rule from which we can predict the weight of a person with the height. Perhaps it should be the other way around, but well, this is now how I implemented it. But you can also do the reverse case, that you measure the weight and the height, and you want to predict from the weight the height of the person. And one way, so you have to specify how to achieve this. And one way to achieve this is by looking at the following objective function, where we look for a prediction scheme And the prediction scheme we are looking at is simply we combine the information, namely the height of the person, with some perhaps additional term, yeah, some constant, and this combination steered by the theta vector should be as close as possible to the target value, the weight of the person, yeah, the y. And this should hold for every I pair, and we penalize here deviations from our prediction scheme, yeah, the theta transpose xi, which is more or less our prediction, how we want to predict with the information from person I, the weight of the person I, and this is penalized quadratically if we have here a deviation. Yeah, so the closer we are with our theta b transposed xi to the yi, the better, of course. And we sum this up over all of them. We normalize it here to make life easier. Of course, this term here is simply a constant, which is not relevant for the optimization with respect to the theta. And we can also conveniently write it in the following way, where we multiply the matrix storing our information with the parameter theta we want to find, subtract from that the y vector where all the target values are stored, and look then at the squared Euclidean norm of this thing. And this is the so-called least square estimation objective. Yeah, so least squared, you see here the squaring, and what you want to do is you essentially are trying to fit a linear function or a hyperplane through the x with the help of the x values, such that the y values are as close as possible to this hyperplane. This is what we are essentially doing. And what we can say about this objective function is we can derive a couple of things about the function. First of all, it's a well-conditioned function. Well, not surprising. We have here the if we have it in this representation with the squared Euclidean norm, this is a quadratic function with respect to our parameter theta we are interested in. And well, if the quadratic function is not well conditioned, then in what a world we are living then. But of course, it's well conditioned, and we can also specify the parameter beta, which is more or less of interest for the gradient descent in this case. And it is, you can check this also analytically if you want, but you can also trust me, the beta parameter is nothing else than the squared spectral norm of the information. Wait, there's a bug. This cannot be true. This should be transposed, sorry. Yeah, of course, this should be a quadratic matrix, yeah? And here you have to transpose the matrix X and multiply it with the matrix itself. You get a quadratic matrix, and from this you can compute the spectral norm, and the spectral norm itself is the square root of the largest eigenvalue of this matrix, which is, by the way, also symmetric. Yeah? So X transpose, if you transpose it once again, you have the same matrix. All right, yeah, so this is the beta parameter. We can also derive the Lipschitz constant in this case if we restrict to the case where the solution space theta is constrained, and the constraint we are looking at is, well, it's inside the Euclidean ball of radius b. Then we can also specify here or at least we can say what an upper bound for the Lipschitz constant is, and we can simply use this upper bound as the Lipschitz constant. All right, then I'm talking again too much, I guess. We had a couple of helping functions beforehand, yeah. So this is helping you to loading the data, to standardize the data, also to do a couple of fancy visualizations, etc., etc. And then the important thing is happening here. So this is where we load the data. Yeah, so we have here the load data function, which is specified above, which is then loading these weight and height values in the, where is it? Somewhere is this CSV file. Somewhere here the CSV file is specified. I don't remember. Not so important. We can then standardize the x values to have weight and height more or less on the same scale. Yeah, otherwise we get in trouble. So standardization is always a good idea. And we can look then at our number of persons for which we have measured the height and the weight, 10,000. And the information we are storing is two-dimensional. Why is it two-dimensional? Because in the X matrix, the first column is simply filled up with ones, because these ones are giving a constant term to our linear function we try to find essentially with the least squares estimation. And the second column is then the height of the person. Okay, then this is where the task began, namely we want to compute the objective function. X theta ai is the input, which is nothing else than short term for this vector, which is occurring in the objective function. So in the very last representation, we had exactly this expression x, matrix x times theta minus 1, minus y, and then the squared Euclidean norm of it. And well, this is what we get if we simply do squaring the entries, computing the mean, and then multiplying with 1/2. You could also, so there are many ways to do this. You could also simply look at the dot product of this vector with itself, and then dividing by 2 times n, but this is giving you essentially exactly the same value there. Then we can compute the beta constant, so the smoothness constant we had here, for which we make use of the eigenvalue calculations, because in the spectral norm of a matrix we have to compute the largest eigenvalue. We first compute the eigenvalues, get the largest one, and then we have to divide this by the number of observations we have. There's also an alternative way. Again, there are many ways to implement this. We choose this one here. We can do essentially the same, very similar to the beta constant calculation in order to get the Lipschitz constant. Here, in fact, I used the alternative way to do this. We have only an additional term in the Lipschitz constant compared to the beta one. And also we multiply here with this b, which is the radius of the ball where we are restricting the solutions to. Then we want to apply gradient descent. So what we need to do is we have to compute the gradient of the objective function. The nice thing about the objective function, it's a squared quadratic function. By now, we should know how to compute the gradient of such quadratic function. We can compute it quite easily, and it is given in this way, which we implement here. Also, this is exactly what you see here. X, t, this is that one, xt. We do the dot product with x theta y, and x theta y is shorthand for this one, which you see also here. And then we divide here by n, and n is equal to the length of x theta y. So this is an n-dimensional vector we get here. Okay, and then the most interesting part perhaps is how to compute the gradient descent. Well, it's quite easy to do this. So this is not a very complicated algorithm. So it's a iteration procedure specified by this line, more or less. So the theta is updated by considering the current theta and going with step size gamma depending on the iteration we are currently in. So this is what we in the lecture always call the t, the iteration, the current iteration, and multiplied with the gradient. Gradient is computed via our function here, compute gradient, which we get as the first input. And well, here we computed also the x theta y value here, which we can conveniently also return as a second return statement, which we get here. And if we have this here, we can plug it into the objective function, because this is how we specified the objective function, that we simply already plug in the x theta y vector, or x theta minus y rather. And we do this a couple of times. So to be more precise, we have a maximal iteration number, which is a parameter of the gradient descent here. We keep a couple of, we track a couple of things, namely the evolution of the thetas, of the iteration of the solution candidates, and also we track how the objective function is changing over the time. This is stored here in this objectives list, which we are extending here after each iteration. So the thetas list is extended by the new theta we get here, and the objective list by the objective, the evaluation of the objective function at the current one. And well, to see also in text form how this is changing, we have here this print statement, which will show us how the gradient descent is evolving. And then we can run this thing. And we want to run this. I have forgot to load it. We can run this with a very naive choice for the step sizes, namely we simply use a constant step size of 0.3. We can also do something different, doesn't matter. You can also play around with that and see what's happening. Let's keep 0.3. And this is our function or functional parameter for the gradient descent, so that the gradient descent is knowing, okay, every time I do a step of size 0.3 into the direction of the negative gradient. We start with our theta as the zero vector, quite common if the zero is involved in the solution space. Another way is to randomize the starting position of the theta. Yeah, so here we will simply use the 0, 1. And we can run this. We can also keep track of the time, the overall time we need to do the gradient descent iteration here. And what we see is all of the iteration evolutions, which are essentially how the objective is changing over the time. So we see we started here with a very high objective value. It's not surprising because the zero vector is perhaps not a good idea, but then we see a lot of changes in the very first iterations, and then almost no changes anymore. So somewhere at the last parts there are some changes. Here there is a change here, and this was very fast, of course. So, and it's no surprise. Gradient descent without projection, of course, is quite efficient. We can also visualize this. This is all these helping function, what the helping functions were for. You can look at how the thetas are evolving with the iteration numbers. So in iteration number 4, we are already quite close to the optimum point, which is the star, of course, and you see we get closer and closer to that. And well, at some iterations there is, at the later iteration, there's even no change anymore. Then we can also tune the choice of the step size by taking the Lipschitz continuity into account, where we have now a new, more sophisticated choice for the gamma step sizes depending on the Lipschitz constant. We have specified the choice in the lecture, and what we see here is again a lot is going on in the first iterations, and well, also till iteration 40, and then it is slowing down more and more. So we are getting closer and closer to the optimum value. And again, we could illustrate this iteratively, what is happening. And you see now we are coming closer and closer to the minimum, and even closer than for the naive step size. Of course, in a naive step size, we could have the problem of jumping over the minimum. Then we can also tune the step size even more, taking into account that the objective function is well conditioned. For a well-conditioned function, we know from the lecture, so this was in one table where we had the bounds on the average error for the gradient descent, and there we saw the optimal choice for well-conditioned function is 1 over the smoothness parameter, so 1 over beta, and beta we calculated before. And here we just use 10 iterations, because after only one iteration, we are more or less already there. So we have no changes anymore. I mean, we could also look at 50 as before, but well, here you have everywhere the same value. And you see when we do simply one step, too much, one step, we are already very, very close to the optimum. We can also look at the evolution of the objective function. Yeah, so what is their value? And what we see is for the smoothness, so where we have the smoothness involved, we are going down very quickly. With the Lipschitz choice, we are going down quite smoothly. With the constant, but this is interesting, we are actually even going down more quickly than with the Lipschitz choice. This is so this is perhaps by coincidence, because the constant step size 0.3 was in fact here a good idea. If we do something different, 0.1 or something, quite slow step size, then it might also happen that the constant step size is above the Lipschitz choice. Also, the Lipschitz choice was rather conservative. So we used here a quite conservative upper bound for the Lipschitz constant, which is then slowing down the convergence. So we could also use something smaller, in fact. So
that means the upper bound is essentially another hyperparameter that we need to tune.
Yes, exactly. So this upper bound could be also considered as another hyperparameter which you can tune, or if you do this more strictly, so this is as I said, quite a rough upper bound. You can also derive here something which is stricter, and then everything will be fine again. The thing is perhaps that the B, which we used, 25, this is making perhaps life hard if we use here 3. This is not better. Wait, we have to make it larger, right? Yeah, exactly. We make it larger. So even more more conservative, because we have here B divided by something where the B is also coming into play, but only in one part of that. So we are making the overall step size even larger if we make the B larger. And now where was it? There. You see that the objective functions are decreasing more drastically. And if we now plot it again, the red line for the Lipschitz choice is now also smaller than before. We could also make it larger, and what we see then is, so the crossing is somewhere there. But this is also quite interesting, perhaps, so that a constant step size is quite naive, but might also work quite well. Of course, this is a quite simple objective function. So it's a quadratic objective function. Their constant step size is working well. So the entire function, so how the landscape is looking like, is quite nice. But if you have a more complicated objective function, then a constant step size might not be the best idea. There could be issues with that. All right, so I over the time quite a bit and still not finished. So what we have here, in the rest is another data set. So concrete data set where we have now only 1030 measurements with the higher dimension. We can do the same things as before, choosing the gradient descent steps with the help of a naive choice, the smoothness choice, or the Lipschitz choice, and we can again plot what the objective function would look like over the iterations. And again, a quite similar picture as before. The smoothness choice is going down quite quickly. Constant step size is working very well here as well. And the Lipschitz choice is lagging behind a bit. But again, if we make the B parameter larger, this can be also, this can come closer to the blue one or even be better than the blue one. All right, so I don't want to go too much over time. Again, sorry for the bug at the beginning. This is where we lost a bit of time, which we now don't have for the practical exercise. So a couple of things we have to do in the next exercise course. So perhaps I will keep the next exercise sheet a bit shorter, that we don't run into time trouble. I mean, it's not a problem because for the Frank-Wolfe algorithm, the exercises can be quite tricky. This is because then a good idea to perhaps keep it shorter there. All right, good. Then thanks for your attention, for watching. I will stop the recording.